consider to be potentially useful to an attacker. So load library is just an example, which is very well illustrated here. Now, instead of bypassing userland hooks, we can get a little bit, we can do a lot more interesting things. And since userland hooks run in ring 3, just like our shellcode does, we can just go ahead and attack our code directly. We don't have to bypass it. We can just get rid of it altogether. So instead of bypassing the hooks, we can just attack the protection mechanism. And this applies not just to buffer overflows. This applies to all security mechanisms that are implemented in userland, such as Win32 Safer. Here's an example. As I mentioned before, when load library is hijacked, well, when any function is hijacked, the first 5 bytes are replaced with a jump instruction. Well, there's nothing that stops us to replacing the 5 bytes back to their original value, which negates all the protection once again. So in this particular case, it's kind of a pseudocode, but it illustrates the point very well, and it demonstrates several techniques that can be used to bypass this particular security mechanism. What we're going to do is we're going to find out where load library is called, and then we're just going to replace the first 5 bytes with the original value. Pretty simple. So the first technique is, first of all, we need to find out where load library is loaded. And to do that, we can use a Win32 API, which is called getProcAddress, which basically gives you the address of any API you're interested in. And the problem is that most of HIPS vendors will probably hook getProcAddress as well, so we cannot use it because we cannot use it because of that. But if we provide our entire copy of getProcAddress in our shellcode, we can just call that directly, and once again, we bypass any type of verification. So all we do is we include getProcAddress in our shellcode and call that. Once we have the address, we just go ahead and replace the 5 bytes with the original 5 bytes, and then we call the load library directly, and this without any hooks or anything like that. Interestingly enough, some of the implementation we've done, well, you might say, well, hold on a second. You're replacing 5 bytes in a code segment. I thought code segment was read-only. But you see, when HIPS vendors when they install their hooks, they need to obviously make the code segment read-write in order to install their hooks. And guess what? They leave it read-write, so we can just go ahead and conveniently override our code segment, which is now read-write and not just read-only. So this code actually works very well against some of the implementations we looked at. Bypassing kernel hooks is a little bit more interesting. And the reason for that is we cannot modify, we cannot tamper with kernel directly. We're not allowed to override any kernel code. We're not allowed to do a lot of different things we can do in userland. So if the kernel is implemented correctly, that's pretty much negates all of the techniques that we just talked about. But there's still a pretty powerful one. The problem with kernel implementations is that kernel implementations still depend on user-controlled data. They still depend on information that is on stack. And the information on the stack is, of course, completely controlled by malicious code. Thus, when malicious code begins to execute, they can create arbitrary fake stack frames. They can do anything they want on stack. And kernel has to trust whatever it sees on that. So to bypass kernel hook, the way kernel hooks work is they rely on stack backtracing. Whilst in userland, if we hook kernel32DLL, we have immediate access to the last return address, which is usually where our shellcode is. The problem with kernel is that it's several layers away from the actual code, from the actual origin of the call. So what kernel has to do is it has to actually find where the call originated from it. So it has to get back all the way to the application. So it takes the address of NTDLL, then it says, OK. It goes all the way to kernel32DLL, then it goes to the shellcode, and then says, So it's writing from a read-write memory segment, so it must be something malicious happening. So the way it does this is relies on stack backtracing. And stack backtracing relies on EBP register. On x86 architectures, EBP register is used just for that, for linking stack frames with one another. Since the stack frame can have a pretty much arbitrary amount of space allocated to it, there's no way for us to find where the next stack frame is without the EBP register. Unfortunately, due to register pressure on x86, a lot of compiler optimization actually throw away the EBP register, or rather they don't use it for the original purpose and they use it for whatever other means. So that pretty much negates this technique completely, even without us trying to do anything. It basically does not work on certain service pack because the EBP register is not there and kernel basically cannot get all the way back to the application. But even if it can get all the way to this particular point, there's nothing that stops us from creating fake stack frames. So all we have to do to bypass the kernel hook is create a fake frame that does not have the EBP register. That is, our stack backtracing is going to terminate at that particular point, and the return address must point to a read-only segment. So it cannot point to a writable segment. So creating a fake frame without EBP register is pretty simple. You just push a couple values on stack and you're done. The only point here, the only interesting point is, well, how do we get a return address that points to a non-writable segment? The problem with this is that we obviously cannot write to read-only segments. So where do we get an address that points to a non-writable segment? Well, the trick here is to actually proxy our return through a ret instruction. A ret instruction is return instruction x86, which fetches a value from stack and returns to that particular value. Let me illustrate this with an example. Here's a little snippet of code that actually bypasses kernel hooks. All it does is, once again, I'm going to illustrate in a load library. The way it's going to work is, instead of calling load library using a call instruction and thereby creating a normal stack frame, we're going to create our own stack frame. So in fact, we're going to create two stack frames, one of them for load library call and the other one for faking and bypassing kernel hooks. So to create a first frame with our real return address, we use the first push instruction. And then we actually emulate a call load library call. But instead of using our normal return address in a read-only and read-write segment that is on the stack or on heap, instead of using that address, we use address somewhere in a read-only segment, and we can find this dynamically at runtime. So we find a ret instruction, and we just use that. So what's going to happen is we call load library. Our kernel hook is going to get all the way to our fake frame. It's going to look at it and says it points to a read-only segment, which means it's OK. There is no EBP register, which means we're going to terminate here. So it looks like we're good to go, and it's just going to allow the execution. When load library returns, what is actually going to happen, it's not going to return to our shellcode. Rather, it's going to return to the next frame, which is going to get our real return address from stack and actually return the control back to our shellcode. So a bit of a trickery here. So here's an example. A normal stack looks like this. Normal stack is the one on the left, where we have two different functions that call each other. Function 2 takes two parameters. It has a return AP address of whoever called function 2, and it's got a saved EBP, which points to the next frame. And it looks pretty much similar. It's got two parameters, a return address, and EBP. That's pretty much how a normal execution goes. Now, like I said, there's nothing that prevents us from creating arbitrary stack frames. So instead of doing a normal looking frame, what we're going to do is we're going to create a frame that, one, does not have the EBP register. Basically, we're going to terminate the kernel stack backtracing here. And two, the return address is going to point to a read-only segment. So here is the code from the previous slide that's actually going to generate this particular frame. Notice that in using just 4 simple instructions, we can completely bypass the kernel hook buffer overflow protection. Pretty simple, just a little bit of trickery, but very effective. And this particular technique also works against userland, since userland pretty much relies on the same mechanism. But there are much easier ways to bypass userland hooks, and this pretty much is only used for kernel stuff. Now, are there any questions when it comes to this? I know this might get a little bit tricky. So are there any questions about how this works and why this works? You guys are sharp. So to summarize, buffer overflow protection is hard. It's very hard to implement it in a secure manner. It's even harder to do it on a closed source operating system such as Windows. The majority of the protection mechanisms that we looked at that are available in the market and are marketed as being effective against buffer overflows are simply designed to detect shellcode. So they don't actually prevent buffer overflows. What they do is they basically try to detect when shellcode begins to execute. And if your particular IPS implementation does this, then you pretty much might as well give up, because it's simply not going to work, and it can be easily bypassed by attackers. Now that we gain access to our system by bypassing buffer flow protection, let's look at how we can cause further damage once our code is running in a system. So operating system protection is designed to protect the underlying operating system. Like I said, it can be Windows or it can be Unix. And it usually involves protecting integrity of system files, system logs, system binaries, registry keys, pretty much anything that can be that's deemed sensitive, that can be used to elevate higher privilege, get higher privileges, or cause any type of further damage. Operating system protection should also disallow loading of arbitrary code. If that is not the case, then you might as well also give up, because once an attacker loads a kernel module, then game over. Once a malicious code starts executing in ring 0, then game over, because it has access to every single resource on a computer, can do anything it wants. And similar to buffer overflow protection, operating system protection can be implemented in user land, ring 3, or kernel. Now, as already described, user land protection is pretty much useless. It runs with the same privileges, thus it cannot provide any extra protection against malicious code. I was disassembling some kernel 32 functions, and I've noticed that Win32 Safer seems to be implemented this way. And I came to the conclusion that this particular technology cannot be relied on once your malicious code starts executing. So it's completely ineffective against malicious code. So if malicious code starts to run, then this is not going to stop any determined attacker. So to do this properly, one has to do it in kernel, in ring 0. The reason for this is the kernel code runs with different privileges. It runs in ring 0. It has complete control over the entire system. It acts as a guardian for all of resources. And it's also very hard to attack directly if implemented properly. You cannot overwrite kernel code. You cannot do a lot of things you can do in user land. So pretty much the only way to bypass operating system protection is to evade it rather than attack it directly. So let's, for example, look at the file system protection. An IPS system, for example, might be designed to protect system drivers and disks. We might say, well, we don't want attackers to override our system drivers. So an IPS system might be designed to protect C Windows System 32 drivers. You might make them read-only and say, no, we're not going to allow anyone to override our drivers. The question is, if it's protecting C Windows System 32 drivers, is it protecting X drivers? Or is it protecting this weird thing? What is X drivers? Well, an X driver is basically a link, a symbolic link that points to the same directory. So to do this, we don't have to program anything. We can just use a simple DOS utility called subs that can map arbitrary drives to arbitrary directories. So let's say we want to override IP filter driver to gain access to ring 0. So since we cannot override C Windows System 32 drivers files directly, we're going to try to trick the IPS system by creating symbolic links. Specifically, we're going to call a subs command, which is going to map X drive to C Windows System 32. And then if you look at the next line and we do dir on X driver's IP filter, you're going to notice that the file that we're actually displaying is absolutely the same. Even though it now calls something completely different, it is now X Windows System 32. Another point, which doesn't involve symbolic links but still is interesting, is X driver's $data. Well, you might ask, what the hell is that? The thing is that due to some Macintosh compatibility issues, which was important, I guess, about 15 years ago, but not anymore, Windows NT was designed to support multiple streams in a file, meaning that each file can contain multiple streams. A stream is basically just a piece of data that can be saved under a particular name. Now, when you access a normal file, let's say you open a text file in Notepad, by default, you're accessing a default stream, which is called data. Now, you can have other streams in there, which are might be completely invisible. And the question is, can your IPS system handle multiple streams? Or is it just working, does it only handle the default case? There are many other attacks that are related to file system, but those are just some of the things to get you to start thinking about some of the ways to attack IPS systems. Absolutely the same mechanism can be used to bypass any kind of registry protection. So let's say an IPS is trying to protect certain keys, certain system keys from being overwritten. So it can be a registry machine system or whatever else. The question is, once again, is it protecting my registry machine system? Well, what is my register machine system? Basically what it is, it's a simple symbolic link that can be created with this particular API. And what it does, it creates arbitrary symbolic links in kernel namespace. So here you see that my registry machine is an object in a global namespace, which is a symbolic link to registry machine. So therefore, my registry machine system / whatever key is the same thing as registry machine system whatever key. And there are some IPS systems that cannot handle symbolic links and can be easily bypassed using this particular technique. Now, what about kernel code? Does your IPS system stop kernel code from being loaded? Well, let's look at some of the ways that one can load kernel code in a Windows environment, and you'll be truly amazed. The well-known and the best understood interface is, of course, Service Control Manager API. And that's used for loading system services. You can be used for loading system kernel drivers, whatever else. So most of, obviously, IPS system can handle that since it's an interface that's most likely to be used to load a kernel driver. Well, alternatively, if that's actually hooked, then you can use a different interface. You can use a ZW load driver system call and try to load the driver directly. Or you can start getting really tricky and start using this obscure system calls that no one really knows why they're there, but can load kernel code nevertheless. It's ZW set system information. There are instances in the past that were published where some of the IPS vendors were able to handle SCM API. They would even hook this particular interface, but they forgot all about this piece of code, and that can be used to load arbitrary code. But that's not all. Besides using little-known interfaces such as ZW set system information, which is quite effective, attackers can get really tricky, and they can try to inject code by directly modifying kernel memory. Windows NT exposes a certain device driver called device physical memory, which exposes the underlying physical memory. So if you have administrator rights and you can gain access to this particular device, you can pretty much start overwriting physical memory. That is, you can overwrite kernel code, you can overwrite arbitrary data structures, pretty much anything else. Also notice that whilst the official name is device physical memory, we can still access it, for example, through my physical memory just as well. Another way, which is pretty much the most effective, the most stealth, and pretty much unstoppable, is a kernel overflow. If one exploits a kernel overflow, they can pretty much inject arbitrary code. And there's nothing, absolutely nothing, that an IPS system can do to prevent this. I'm not aware of any, or at least of a lot of kernel overflows in Windows NT, but I'm sure there's some. Another interesting point is that an IPS system cannot simply prevent all processes from loading kernel code. The reason for this is that some system services rely on the ability to be able to load kernel code, to load kernel drivers to carry out whatever tasks. So some system drivers, or some system services, must still have the ability to load kernel drivers. Well, one way some IPS vendors approach this problem is say, well, we're just going to trust particular system processes. We're going to let them to load kernel drivers. Well, guess what? All we have to do is we can use old and trusted DLL injection technique to inject our userland code into the trusted process and then load malicious kernel driver while it's running in the context of a trusted system process. Another technique is to modify an existing kernel driver in disk, which is why I was showing you the example with symbolic drivers. Whilst an IPS might try to make some device drivers read-only, we can still possibly bypass it and just modify driver on disk, and then on next reboot, we got code running in ring 0. Another interesting possibility is, instead of trying to open a file, can we just open the device card disk partition, which is basically like dev HDA on Unix, and modify raw code on disk? That's a very powerful technique, and I didn't see a lot of people talking about it. So, as you can see, there are some official ways, but there are many, many other ways to get your code to run in the kernel. And like I said, once you have malicious code running in ring 0, it's game over. So to summarize the OS protection bit is, IPS systems, well, most of them are designed to protect the underlying operating system, the integrity of the operating system. System logs, registry keys, et cetera, et cetera. User-land implementation cannot be relied upon because they run with the same privileges, as I pointed out before. So any decent IPS must rely on kernel implementation. So kernel implementation is a lot more robust. But whilst they cannot be attacked directly, they can be still evaded by modifying system namespaces, and we can get tricky and try to load arbitrary kernel code, which is pretty fatal. Any questions on the OS protection bit so far? Okay. Besides trying to protect against buffer overflows, trying to protect the underlying operating system, a very important point is protecting itself. A security mechanism that tries to protect everybody else must also protect itself. And a lot of vendors seem to forget about that. So a HIPS system might be attacked directly. So appropriate services or daemons can be attacked directly. A service can be simply unloaded. You can just go into Service Control Manager and say, stop this particular service. And if there is no self-protection code, then pretty much your protection stops there at a simple click of a stop button. On Windows, we can get a little bit tricky, or even in some instances in Unix, so we can try to tamper with the memory address space of a running agent, HIPS agent. So for example, we can use APIs, Windows 32 APIs, such as read process memory, write process memory, to try to tamper with our running agent. We can try to modify some of the data structures. We can try to do other tricky things. Or we can get really aggressive and just inject our own code into running service. There's nothing that prevents us from injecting our code into the service and then completely taking over the security. Unfortunately, I don't have a demo of this, but I've been talking to some people, and they told me that it's possible to attack certain IPS, which shall remain nameless. It's possible to inject code into running instance of this particular IPS because it does not control read process memory and write process memory. We can inject code into the service and then use, whilst running in the context of the process, we can actually unload the kernel driver that enforces the security, or we can basically stop all the hooks. We can disable all the hooks, or we can pretty much do anything else. Or we can just take over the entire job and just say, well, if this particular process is running, then always allow it to run. So the point of this is, if IPS does not protect itself, then it cannot obviously provide any type of integrity for the rest of the system. In conclusion, as I mentioned, I do believe that HIPS technology has a promising future. But getting it right is quite hard. There are a lot of attack vectors. And missing just one, for example, missing just one way of loading kernel code completely compromises the security and integrity of the underlying system. Missing one way of getting the kernel code, malicious kernel code, to run in ring 0 pretty much compromises the entire system. So it's quite hard to get it right. And the majority of current IPS implementation suffer from a variety of security flaws. They make a lot of claims, which unfortunately don't stand up. Specifically, providing effective buffer overflow protection on Windows is very, very hard. And as I showed you, some of the IPS players can be trivially bypassed. So IPS technology has a promising future, but it needs time to mature. And it might need some help from OS vendors like Microsoft to get things right in terms of when it comes to buffer overflow protection. Now, if you have any questions, I'll take them before showing you a little demo. So if there are any questions so far, I'll take them now. Yes? Right. The question is, what is the preferred method of getting the code to run in the kernel? Well, the easiest way is really use a very little known interface such as EW set system information. Until recently, most of the people weren't even aware of its existence. And so it was really trivial. I think Greg Hoagland was one of the first ones to point it out with IPD about 2 years ago. But I have not tested other other IPS implementations, but I'll bet you some of them can be still bypassed. And unfortunately, it's a very, very hard job. Like I said, there's nothing that stops anyone from exploiting a remote service, gaining control, gaining administrator rights, and then opening a device partition directly and modifying a driver on disk, and then rebooting the machine. And after that, you've got ring zero code. And that kind of attack is really, really hard to prevent. Even without loading kernel code, if you got malicious code running in your system, then you're in deep trouble. And so since there are almost no decent implementations of buffer overflow protection, it's a really hard problem. Yes? Right. 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 A gentleman suggested a different way of protecting buffer overflow, specifically hijacking APIs and then putting kind of a wrapper around them, which has a counter. So it says, I've called this function once, or I've called this function twice, and then when you return, we make sure that the that the counter is still correct. Now, I've seen your post to BugTrack, and I've thought about this, and there are several problems. First of all, this particular myth. Right. The one major flaw, which has nothing to do with security, is handling asynchronous code, such as exceptions, such as signals, etc. So basically, if we tear down multiple stack frames, then that pretty much kills any kind of counter. The other problem with this approach is, like I mentioned, if your code is running with the same privileges, and you're trying to basically create a security mechanism that runs with the same privileges as your malicious code, then you might as well give up. Because that's more or less security through obscurity, because you're creating a system which does some magic things. But like I said, once the code starts running with the same privileges, there's nothing that stops me from creating arbitrary stack frames with arbitrary canary values that I control with arbitrary counters. So there are issues with that particular scheme. Right, you have to find the counters, but I've seen weirder things getting exploited. So, are there any other questions? Yeah. The question was, does this also apply to Unix systems? While some of the stuff that I showed was mostly geared towards Windows system. Like I said, the architecture is not that different, and if implementations are pretty much done the same way, then you can attack them the same way. As a matter of fact, I've talked to some people who implemented the systems on systems like Solaris, and they use similar techniques for protecting. Therefore, we can use similar techniques for bypassing. And as a matter of fact, Unix architecture is a lot simpler, so there are other ways of attacking the code. So Unix is different, but it's not that different. So you can pretty much use the same techniques. And so if it is on a closed operating system such as Solaris, you're going to run into the same problems where you don't control the operating system. So you have to use various tricks, such as hooking various functions and then doing some magic in the background. But yeah, this pretty much directly applies to Unix systems as well. Yeah. Right. I'm sorry, would I install it? Right, like I said, I don't want to say that HIPS is just a buzzword and it's basically going to go away in a couple of years. In fact, I strongly believe that this technology has a promising future because security belongs in an AND host, because this is where it actually happens. So a properly implemented HIPS system has control over the entire system. So you can do a lot of different things which you can do never in the network. Now, the question was, well, would you still recommend a CTO of a large organization who has 5,000 workstations to actually implement this kind of technology? And it really depends on, whilst the technology really matters, it also you have to consider risk management, you have to consider the costs. And so you might find that maybe a network-based IPS or IDS or whatever might not offer the same type of security, but it costs 1/10 of the entire solution. So it really depends on what you're trying to do, what kind of threats you're dealing with. I like IPS. I really believe that they have a place in modern companies. But like I said, it takes time to get it right. It's really hard. What I covered is really just the top. This is just protecting against simple things. It's protecting against buffer flows and protecting underlying operating system. When we get into protecting applications, when we get into starting analyzing the system calls and what applications are allowed to do, things get really, really hairy. Windows, unlike Unix, has very interesting, quote-unquote, interesting architecture, and it does a lot of interesting things. And once you get really low level and you start looking at system calls, things can get really, really interesting. So there are a lot of different values to consider, a lot of different issues to consider. And like I said, technology needs time to mature, really. It's quite, in terms of commercial offerings, it's really quite new. So there's still some issues that need to be ironed out. But I do believe that we'll see, we already see some installations of systems, even though they're vulnerable, they're out there. But I believe that we'll see more and more of them as technology gains more acceptance and the implementations will get better. I do believe that we will see more of them, at least, for example, on sensitive servers, if not across the entire enterprise, such as across 5,000 workstations. Yes? The question was, how effective is the no execute feature that's implemented in the latest AMD and then picked up by Intel? The no execute feature consists of adding an extra bit, which is about 30 years overdue. But in particular, the problem is that that x86 processors, such as Intel and AMD processors, do not support execute bit on pages, meaning that you can make a page read-only, you can make a page read-write, but you cannot say that this page is not non-executable. You cannot say that your stack segment, you cannot execute code from your stack or from your HIP. This is why we have this convoluted solutions, such as providing quote-unquote solutions by trying to detect whether we're writing from a writable page. Well, what IPS vendors are trying to do here is do the no execute bit. Because if we had the no execute bit all along, all we have to do is say stack and HIP are non-executable. And pretty much we don't have to hook anything because the underlying processor will enforce this particular feature. Now, how effective this feature is, well, there are several issues to consider. First of all, in short term, it's not very effective because it only works on 64-bit processors, at least on AMD. So if your workstation or your service are not running an AMD 64, it's not very useful. Second of all, only certain operating systems support it. I'm sure a Service Pack 2 will support it and 2K3. But if you're running 95, don't bother. And third of all, the technology, some of the buffer overflows, some of the integer overflows will not be stopped by this particular feature. Yes, normal, simple stack overflows will be prevented, but there are other ways of bypassing this feature. So basically what it's going to do is going to raise the bar for existing technologies. Yes, it's a good idea. It will take time for it to mature, for it to get out there. It's a good idea, but don't count on it just yet. And also going to put some IPS vendors out of business. So they are backporting back to 30-bit processors. Intel. Okay. Well, the thing with Intel and Microsoft, it took them 30 years before they started taking security serious, and now they have to play a catch-up game. And they're going to cost them a lot more money. But nevertheless, things are improving slowly but surely. Multics was designed in the 60s and it was done right, and pretty much everything after that was done not right. But we'll not get into that. Any other questions? Okay, I'm going to show you a brief demo. First of all, I'm going to run really quick through a simple kernel 32 hook. What I did is I wrote a simple code that emulates the hook feature. That is, it gets the return address from stack and makes sure that it's not on a writable page, and then if it is, then we pop up a message box, and if it's not, then we just go on. So this is basically to demonstrate. I know that it might be a little bit hard for me to explain the entire feature in 3 slides, so I'll think if I show it to you live, it'll illustrate a little bit better. So what's happening here is we have a function which is called buffer overflow protection. And what it basically is, it's a simple kernel 32 hook or NTDLL hook. All it does is it retrieves the return address, which is the first D word on stack, which has been pushed there by a call instruction. It retrieves the return address from stack, and then it does a pseudo check against to see whether it's on a writable page. What it actually does, it makes sure that it's not on stack. The stack on the Windows 32 of a primary thread is below usually the binary base address. It's a hack, but it doesn't really matter. Let's step through the code and see what's going on. So the first instruction here is going to retrieve the return address on stack. Like I said, it's the first code D word on stack. If we look at the memory here, I hope you can see this. The first 4 bytes is our return address. You can actually see it in the registry window. And the value is 12FD08. And 12FD08 is a stack address. It's a stack address, so it's under the binary base address. So this should basically work, and we should flag this as a buffer overflow, or rather as something running on stack. I should mention that there are some programs that do actually create code on stack and run it from there, such as Java. Java generates some of the code at runtime on stack and runs it. So as a matter of fact, this particular implementation is going to break some of the Java applications. So nevertheless, we retrieve the return address, and then we do our little check, and it fails. So we say that buffer overflow has been detected. We terminate the process, and we just go on. So this is pretty much how the IPS vendors designed this. So they get their return address from stack. If it's writable, then that's it. We got a buffer overflow, end of story. Now, using identical code, identical shell code, that instead of using a stack-based return address that uses our proxy through ret technique, but otherwise remaining the same, bypasses this code and bypasses many other IPS implementations. So same code, just a slight difference. The difference is that now when we execute the return address fetch, if you look in the register window, what the value actually is 4148 FB. Now this is above binary base address. What it actually is, basically, it's not on stack. So this passes the non-writable check, and it passes a no EBP on stack. This terminates all stack backtracing. And if we step through the code, then we don't get the buffer overflow detected message because our return address is valid. It's not on stack. If we trace further down and we actually look what's on stack now, we get to our second stack frame, which is the one that actually has the real return address, which is 12FCFB. And that's actually is very similar to the original value, which is a stack-based value. And now we execute ret, and we regain control of our program. So this pretty much illustrates how this works in a little bit more details. And so if we continue running, then we're just going to get done, which means that we got to the past the buffer overflow protection. Well, you might say, well, this is just a silly example. You know, I can also throw a couple assembly lines together and it's going to work. The problem is it actually works in practice. Now, I've got a VMware here which has a simple IPS running on it. And it has 2 versions, but it just showed you. One that does not use bypassing techniques. It just calls the load library directly, or whatever the API was. And the other one actually tries to call load library by creating a fake frame. And if we run no bypass, it immediately terminates. And the reason why it immediately terminates is because the shell code, or rather IPS, picks up the fact that it's running off the stack and it terminates it. Executing identical code that uses our fake frame technique, if we run it, it actually is not terminated. As we get the done prompt, which means that we got past, at this point, we have successfully loaded an arbitrary DLL. That is, we executed malicious code in the system. And then if we look at the log of this anonymous IPS, we see that it's a generic buffer overflow on a C no bypass executable, which means that we detected, or rather IPS has detected, that there was a code running off stack. So very simple technique that's very, very effective against a lot of different IPSs out there. So that pretty much concludes my talk. If you have any further questions about this, feel free. And if not, thank you.